Hello everyone. In this video, we are going to talk about hypothesis testing. This is the reading list. I would encourage you to go through these two chapters to know more about this topic. So to begin with, uh, hypothesis testing is one of the most fundamental and important tools in statistics. It helps us answer real-world questions using sample data, and we collect data to see if it supports our ideas about how things work. An important point to remember is that we can't usually prove our theories are correct with absolute certainty. Instead, we test whether our data is consistent with our ideas. This approach is used everywhere. We as economists test theories about markets, medical researchers test the effectiveness of treatments, companies test new products, and businesses use it to make better decisions. So hypothesis testing gives us a very structured way of learning from data. This method works in just one fundamental way. So we always start with two competing hypotheses. First, we have the null, which we usually denote as H naught. This is what we initially assume to be true. Often the status quo or the idea is that nothing interesting is happening. Second, we have the alternate hypothesis labeled HA. This is usually what we are trying to show. This is our research hypothesis or the new idea that we want to support. We collect data and ask, is this data consistent with the null hypothesis? If our data would be very unlikely under the null hypothesis, we reject it in favor of the alternative. It is like saying this data is so inconsistent with our initial assumption that we should consider the alternate hypothesis instead. So it's kind of a negation approach that we take in this framework. So we set up the hypothesis as follows. So if we are expecting a positive effect, like a new teaching method improving test scores, we set up as the null being no positive effect and the alternate being some positive effect exists. If we expect a negative effect, the null is no negative effect and the alternate is some negative effect. These are called one-sided tests because we are interested in an effect in one specific direction, either positive or negative. The parameter beta represents the true effect what we are trying to measure. But sometimes we don't have a specific direction in mind. We just want to know if there is any effect at all, positive or negative. In these cases, we do a two-sided test where the null is there is no effect and the alternate is some effect exists. For example, if you're trying to study how a policy affects employment, but we are genuinely unsure about whether it increases or decreases jobs, we do a two-sided test. We simply ask the question, does this policy matter at all? It is important to understand that we can never be 100% sure about our conclusions. We cannot say whether conclusions are correct or not with absolute certainty. And statistical inference always involves uncertainty. Two types of errors can occur in hypothesis testing. The first is called the type 1 error. This happens when we reject a null hypothesis that is actually true. It is a false positive, like concluding a medication works when it actually does not. The other type of error is called type 2 error. That happens when we fail to reject a null hypothesis that is actually false. It's a false negative, like failing to detect that a medication does work. There is an inherent trade-off over here. Making one type of error less likely typically makes the other type more likely. So we need to balance these risks based on the context of our research. To make our test process objective, we need a clear rule to decide when to reject the null. This involves comparing a test statistic, a number calculated from our data, to a critical value, that is a threshold that we set in advance. The critical value creates a boundary between two regions. The acceptance region, which is where we don't reject the null hypothesis, and the rejection region, where we reject the null. How strict we want to be determines where we place this boundary. This is our significance level, which we will discuss more in just a moment. The t-test is probably the most common test you will encounter, especially in regression analysis. It tests whether an estimated coefficient is significantly different from zero. In other words, whether a variable has a real effect. The test statistic has a simple formula. It is the estimated coefficient divided by its standard error. So beta hat divided by standard error of beta hat. This ratio tells us how many standard errors the estimated coefficients is away from zero. Larger is the t-value in absolute sense. Stronger is the evidence against the null. To use the t-test, we compare our calculated t-value with a critical value from the statistics table or software. These critical values depend on several factors. First, it depends on whether the test is one-sided or two-sided. Second, it depends on our chosen significance level. Typically, it's 5%. And third, it depends on the degrees of freedom. Roughly, it means sample size minus parameters. Our decision rule is simple. We reject the null if the absolute value of the t statistic is greater than the critical value, and the t has the sign implied by the null. For example, if the sign implied by the alternate. So for example, if the alternate hypothesis suggests a positive effect, we reject the null only if t is both large enough and positive. The significance level, commonly set at 5%, represents the probability of making a type 1 error, that is, rejecting a true null hypothesis. Lower significance levels, like 1%, are more conservative and they require stronger evidence to reject the null. Higher significance levels, like 10%, are more willing to reject the null and they require less evidence. When we can reject the null at the 5%, we say that the result is statistically significant. This means that the observed data would be quite unlikely if the null hypothesis would be true. A correlated thing in this context is the p-values. The p-value offers an alternative way to think about the hypothesis testing. It is the probability of observing a t-statistic as extreme as yours if the null hypothesis were indeed true. Lower p-values provide stronger evidence against the null. A very small p-value means my data would be highly unlikely under the null. The decision rule becomes reject null if the p-value is less than my chosen significance level. For example, if my p-value is 0.03, I can reject the null at 5% because 0.03 is less than 0.05, but not at 1% level, because 0.03 is greater than 0.01. A confidence interval gives us a range of plausible values for the true parameter based on our sample data. For example, for a coefficient, the 95% confidence interval is calculated as beta hat plus minus the critical value times the standard error of beta hat. The interpretation is this. If we repeat the exercise over and over again and keep estimating the beta hats every single time, then 95% of the times our obtained value will lie under this interval. Confidence intervals connect nicely with hypothesis testing. If 0 is not in the interval, the coefficient is significant at that level. That gives us a visual way to assess the significance. While t-tests examine individual coefficients one at a time, f-tests allow us to examine groups of coefficients together. The most common f-test is the overall significance test, where the null is all slope coefficients equal 0, and the alternate is at least one coefficient is non-zero. F-tests are particularly useful for testing joint hypotheses. For example, if we include quarterly dummy variables in a model, we can do an F-test to check whether the seasonality matters as a whole, rather than testing each quarter separately. So before we conclude, we must acknowledge some important limitations of hypothesis testing. Statistical significance does not necessarily mean practical importance. A coefficient can be statistically significant but still be too small to matter in the real world. With very large samples, even tiny effects have practically no relevance that have let me rephrase. So if you're working with very large samples, even tiny effects that have no practical relevance can become statistically significant. So there is a risk of getting artificially significant results if you're working with large samples. Hypothesis testing does not test a theory's validity in a broad sense. It only tests consistency with the specific data that we have. And perhaps most importantly, statistical significance does not prove causation. A significant relationship could be due to other factors as well, like reverse causality or coincidence. But that is something that is beyond the scope of this framework. So always interpret your results in the broader context of your research question and with existing prior knowledge. I hope this was useful. Thank you.